Hi guys, welcome back to my channel. Today we're going to be having a quick look at vectors and what they are and how we can use them to solve simple problems. A vector is a quantity that has both magnitude and direction. So for example, the wind is something that has both a magnitude, which is its speed, and direction. So previously we've examined scalar quantities which have magnitude only. So from our example, if we were just looking at the speed of the wind, this is very one-dimensional, and so therefore that's a scalar quantity. Two vectors can be considered equal if they have the same magnitude and direction. So here we can see we have an arrow representing a vector. This here is called the head of the arrow, and this here is called the tail. So that means that if I had another vector that was pointing in the same direction and had the same length, then it would also be a vector that is equal to my vector that I have on screen. Vectors can be represented in a few different ways. Primarily, we can represent them on a diagram using an arrow. We can also represent them if we were doing a 2D arrow, so that is we're only looking in the X and Y direction, then we can represent them using a sort of modified matrix. And I'm a little bit hesitant to call it a matrix because really when we have vectors we generally only represent them using a column matrix, or we represent them using a row matrix. So for example, if I was to have a look at this here, and let's say that this was my Cartesian plane acting here, then this would probably, as a guess, be acting at, let's say, positive 10 in the X direction, and then let's say negative 3 in the Y direction. So this is how we would represent it using a coordinate point. So to change that and to represent it using the vector notation, we can do it using, like I said, a column vector. So we have 10 and negative 3. Or we can do that using a row, so as 10 and negative 3. Sometimes we may also see these arrows that can be used to contain the vector. Now, to represent this, we can also use a few different notations. So we can use a bolded letter. So in this case, we've used the bolded letter A. We can also use a tilde. So a tilde is one of those funny wiggly symbols, and sometimes we'll see this underneath the letter, and sometimes we'll see this on top of the letter. And lastly, we can use an arrow to represent the direction of the vector. So in this particular case, because we're going from A to B, the arrow should be pointing from A to B. So if we were to reverse this, if we were to write this as B A and point it that way, that would actually be implying that this is going from B to A, and this would actually be opposite to this vector. It's acting in the opposite direction, and so we can actually represent that using a negative symbol instead. So here's just a quick example. We've got this vector here from A to B, and again we can use this vector and represent this as a B using an arrow. Alternatively, we can represent this using the vector U. If we reverse the direction, then that means that we are also making this vector a negative. Let's have a look at a simple problem that we can solve using vectors. A plane is flying along 3 kilometers east and 5 kilometers north of the airport. The pilot then receives instructions to travel a further 5 kilometers east and 3 kilometers south to avoid another plane. How far is the plane from the airport? So let's go ahead and let's use our diagram to show the movement of the plane using vectors. To find this total distance going from my airport, which I've defined as the origin, to this final point here, B, I need to add each of the vectors. So what I've done, I've used arrows and this vector notation to represent the vectors. So assuming that east is the positive direction and north is the positive direction, I've defined my first vector here from the origin to A as 3, 5. My second vector here from A to B I've defined as 5, negative 3 because they are moving a further 5 kilometers east and 3 kilometers south. So they're traveling negative 3 kilometers. Now, when I add these vectors, I need to add them in a specific way, and I can do that because these are touching from tail to head and then tail to head. So to find this final vector here from O to B, so that's the vector OB, that's going to be equal to this vector here, so OA, plus this vector here, AB. Now, since this is already in its component form, so what I mean by that, it's got the X and the Y components, all I need to do is add each of these. So this is going to become 3 plus 5, which is going to be 8, and then 5 plus negative 3, which is going to be 2. So this is my position of this vector OB. Now what I need to do is I need to find the magnitude of this vector. Now this is where it gets a little bit tricky, but we can actually use something that we're already familiar with to find this length. I'm going to draw a second diagram just so you can see a little bit easier what's going on here. So as we said before, this vector is already broken down into its components because this X component along here is going to be equal to 8. This vertical component here is going to be equal to 2, and we know that because of this vector here. And so then what we can see, this is going to form a I've done that in a bit of a non-spot, haven't I? This is going to be a right angled triangle. So we can use Pythagoras' theorem in order to determine what the length of this line here is going to be, and therefore the magnitude of the arrow or the vector itself. So let's use Pythagoras' theorem now to solve for this length. So using Pythagoras' theorem, we were able to show that the distance from the origin is going to be about 8.24 kilometers. So that's how we can use vector addition to solve problems, and how we can find the magnitude of those vectors so we can determine the distance from a particular point, which we've defined in this case as the origin. Alright guys, that's it for this video. I'll see you in the next one.